All right, class. We're going to start chapter 7. This is 7.1. We're talking about the normal distribution, um, which deals with continuous distributions. So far, we've been doing discrete distributions, and I want to sort of talk a little bit about that before we actually start with the normal. Okay, so if we had this distribution, first of all of our probabilities have to add up to 1, which they do. And so what would the probability of, whatever this is, I don't even know what this is, having 7 somethings. What's the probability of having 7 somethings in this distribution? It is going to be 60, or 0.6, which is 60%. So what we did there was we just looked and saw how high this bar is. But what we're really doing in this is we are taking the area of this bar, because think about what an area means. Area means base times height. And so how big is this base? Well, we haven't really talked much about this, but this goes from 6.5 right here to 7.5. So how big is that base? That base is 1. So if you were doing area, it's going to be 1 times however high it is. Well, how high is it? It's 0.6. It tells us right there. So it's 0.6. And so the area is 0.6, which is exactly what the probability is. So what we've been doing is we have been finding areas of these little bars. So, but now that we're doing continuous, we don't have these nice little broken out bars. We're going to have a graph with a smooth line that's that might look like that. It could look something else, but really what we're doing still is we're doing the area, except for we're just wanting to find the area underneath that curved line instead of the nice sharp line. So that's exactly what we have been finding. It is the area, is the probability. Okay, so now that's what it says right here, a probability density function. That's PDF for short. Here's the two properties. We just talked about them, and they're the same two properties that we had when we did discrete. The total area under the smooth line now has to equal 1. Which is exactly what it had to do when we had the bars. And the height of the graph must be greater than or equal to 0. So that means you don't have any negatives. That means it's not going to be going down below the line. Okay, just like it does in discrete. Okay, so here's our first problem. It says, suppose that a United Parcel, UPS, is supposed to deliver your package between 10 and 11. This is a continuous situation, because remember, continuous means it's not countable. It's got the decimals in there. So that guy, the UPS person, can come at 10:05, 10:05 in a few seconds. So there's a lot of little intervals in between here. Okay. So what we're going to do to make our little chart is our chart's going to start at 0 and end at 60, because there are 60 minutes in between 10 and 11. And so this is a new little video thing that we're using. So I'm still learning it. So I have to put you guys on hold for a second and move my page down. And I'll pick you back up in a second. Right. Okay, so I moved my paper down. So here's where we are. Like I said, we're going to go from 0 time right here to 60, which means that this is going to be 10 o'clock and this is going to be 11 o'clock. Oops, that's supposed to be a little dot, but that didn't work so well. Okay, so 11 o'clock. Right there. Okay, and then all the time in between. Okay, well, remember what we just said. If the area underneath your picture has to be 1, then that means we have to use the area as 1, or we have to write the area as 1. And also, by the way, I forgot to say this. This is a uniform probability distribution. It's not going to be a nice little curve. It's just going to be a flat straight across, because it is just as likely for him to come at 10:05 as it is for him to come at 10:57 or 10:33 or anywhere in between there. So it's just going to be a nice flat line, just like this. Actually, I can make a nice flat line all the way across to the 60 mark. Okay, so now if the area below that line, below that distribution has to be 1, well, I already know what the bottom number is because it goes from 0 to 60, so that's 60, so that's what we plugged in. Now we just have to get the height, and we just have to do this little dividing. So you just divide both sides by 60. You're going to get h equals 1/60th. So this height right here is 1/60th. Okay, so let's do this problem. It says, what is the probability of falling of the UPS guy coming between 10:15 and 10:30, which would be right about here to here? Okay, well, what time would that be? Well, let's just kind of mark this out a bit. So they're asking us, what's the probability of him coming at this time? Well, what that means is, remember, probability just means the area in this little section. So all we have to do is find the base times the height, which we already know the height. All these heights are the same, so the height's going to be 1/60th. But what's the base? Well, the base is just the time in between 15 and 30 minutes. So it is just going to be 15 minutes. So it's 30 minus 15 times the height, which is 1/60th, sorry. And so that's just going to give us 15 right there times 1/60th. And if you multiply that together, it's going to give you, I'm going to go back up here and do this, 15/60ths, which does reduce. And in decimal form, it's going to be 0.25. So what are your chances of him coming between 10:15 and 10:30? Is you got about 1/4 chance, or 0.25, or a 25% chance. Okay, so that's what this says. The area under the graph is the probability, and it always has been. We just haven't talked much about that little area formula. All right, so on to the next page. Okay, so this page just sort of explains the similarities between a discrete, which has the bars, and a continuous, which has just the smooth shape. But it just says if a relative frequency is symmetric, then it is said to have the shape of a normal curve. And so this bell-shaped curve is a normal curve. Okay, same thing with this one. If a continuous random variable is normally distributed, then it is said to have the shape of a normal, which normal in this case means bell-shaped. And oh my gosh, old. I don't know what I just did. Okay, clearly I am still just learning how to do this, so I don't know why it went sideways on me, but it did. I got it back. Okay, so it's same thing. Here is the smooth shaped as opposed to the bar, but it is still a normal, it is still a bell-shaped curve, which means it is normal. Okay, these things are called inflection points, which I think we will get into a little bit more in just a little while. But basically what an inflection point means is, if you notice on the lower part of the curve, up until that inflection point, that curve is curving opening up. And then from this inflection point to the other inflection point, this curve is opening down. And then from this inflection point on to the end, the curve now is opening up again. So that's what inflection point means. It means when you change from opening up to opening down. And so that's what that means. Like I said, we'll get into that a little bit more in a couple pages. Okay, so the next thing is these are all examples of normal curves. Even these over here, it just means that this little red guy, the red one, has a much smaller standard deviation. That means the data is all nice and compact in a smaller amount. The blue one on the back, sort of in the background, has a much bigger standard deviation, which means the data is spread out a little bit more. This one is also two normals, except for this one has a mean of 0 and this one has a mean of 3, so it just shifts it over. Okay, so let's move along. Okay, so if you have a normal curve, it's awesome because it has all these things. Notice the bottom is a really good one also. But let's just talk about it. It's symmetric around the middle, which is the mean. Okay. Oh, this has a typo, by the way. This is supposed to be a plus right there. So go ahead and make that a plus. Says because it has one peak, and that is the mean, the middle. It is also the median because it is the middle piece, and it's only got one peak, so it is the mode. So they are all the same things. The mean, median, mode are all the same if you have a normal curve. Okay, it has inflection points. That's what we just talked about where it switches at one standard deviation to the left and one standard deviation to the right. So change that one. That's got a type. That's supposed to be a plus. Okay, area under the curve is 1, which we already talked about. Well, this is sort of logic. But if you have the mean and it splits your picture down the middle, that means half of the area is on the left and half the area is on the right. Okay, as x increases, that means as you go down, like for instance, if you go down here, it never quite gets to the x-axis. It just skirts along it. And the same thing over here. I didn't draw it very well, but it's just skirts along that. It never actually gets there. So as it gets higher and lower, it never actually gets to the line, but it does just skirt along. Okay, and then because we have a normal shape, the empirical rule is in effect, which means all that good stuff that we learned about the empirical rule. So if this was our mean and we had one standard deviation out, there's 68% of the area is under there. And this is on your little handout, fold-out thing where all your formulas are. And then there's 95% within 2 standard deviations, which was actually on our last test. But there's 95% within 2 standard deviations. Okay, and then there's 99.7. All these numbers are on your fold-out thing. All right, let's scoot down. So this is the picture of your empirical graph. So shows all the little breakouts. All right, let's go to the next page.